electronic mode this year. I didn't bring Haypress Creek, for instance, to show it off. Sadly, I have not made a great deal of progress on Haypress Creek, as you can tell from my Haypress Creek blog. But I have made some progress, and I want to talk about it. I'm going to be perhaps less technical than you have been hearing all afternoon as a change of pace, and certainly informal, so anytime you have the urge to interrupt me, please do. First off, I want to show you my feet. You've perhaps all seen my feet. 5 Fingers Vibrem shoes, which are extremely comfortable. I hike in them, and it's a lot of fun to hike because you feel the ground underneath your feet. I feel literally when I wear my boots, I am putting my feet into boxes, and that's no fun. I met a guy on the trail last week wearing 5 Fingers, and we exchanged comforting statements. Jeff has 5 Fingers. They're the coming thing. John has 5 Fingers. They're the coming thing. Everyone's to try them. You can get them on the web or at REI. I boasted on my website that I had not had a back problem since I've been wearing them. These have no heels. You are walking differently than you would normally walk with a 1/2 inch of heel on your foot. Makes a difference. But I have had the back problem as of 2 days ago. So there's no guarantee against twinging your back, but it does perhaps reduce the probability. They dry quickly. You can wade in the water and wade out of the water very easily. And I'm looking forward to trying them in the snow. They're remarkably warm, even without socks. But I don't know if you're in ankle-deep snow what that's going to do to them. Yeah. So much for feet. I've had a very busy life this last year. I'm involved in 4 lawsuits at the moment. A 5th one on the horizon. This is extremely tedious and disappointing. It's not the way I want to spend the rest of my life. But I'm getting to know lawyers, and I'm getting comfortable in lawyers' conference rooms. And I'm learning a lot about law, which I don't need to know. And I am thoroughly disappointed in the American justice system. I've a few comments to make about lawyers. I had a deposition a couple weeks ago in Bay Area, Palo Alto, as a matter of fact. At one point, there were 8 lawyers in the room with me, 4 hostile and 4 friendly. This had to do with patent re-exams. The MMP patents are very valuable. They have sold $300 million worth of licenses in the last 5 years or so. I've been cheated out of most of my promised income from that, which is one of the lawsuits. Companies are very unhappy to license patents. They're fighting tooth and nail, especially now. They acquiesced somewhat more easily in the early days, but now they're fighting hard. 3 companies, Japanese or Taiwan, I forget, were arguing about the patents, saying they didn't need to license them. And I was explaining, I was answering questions. I wasn't explaining anything. I've got to keep that straight. They would ask me a question, I would give them an answer. Most of my answers were yes and no, which is very disappointing to a a lawyer who wants you to expand. But that went on for 2 days. Win or lose, who knows? The lawsuit will continue. I am suing Dan Leckrone for $30 million in royalties he's cheated me of. If I had that money, I could do some interesting things with it. Finance green arrays, for one thing. Finance fourth education for another. All kinds of good things. And finish my house. That's a very selfish thing to build a house. Everybody who gets rich does that because they don't know what else to do with their money. It takes you a while to set up a charitable foundation or something. So I built my house. It's cost far too much. It's probably too large, but it's very nice. And I would like to stay there if I can, which is unlikely. It is not finished. It would cost as much to finish as it would to build a house. So that may not happen. But I'm enjoying my time there. I'm a little bit sorry to have come down here today because there's a great snowstorm going on in Incline Village. It's supposed to be 4 feet of snow outside my house when I get back. It's a lot of fun to watch that snow come down. I have many windows and skylights, and the snow is everywhere. Next week, I get to go and negotiate with the bank as to when and if they're going to foreclose. That counts as a lawsuit. Okay, that's a change of pace. Just get back to GA 144, or as it's sometimes substituted, the S40. I told you last year that I was using the S40 to measure temperature. No one has said it today, but to remind you, the GA144 is an asynchronous chip. There are 144 computers on it, each running as they see fit. Nominally, they're all running at the same speed. Greg insists that that speed varies by plus or minus 10%, depending on where you are. I hope that's large. I would expect it to vary more like 1%. But I'm trying to measure this. It is hard to get inside a chip. There's very expensive test equipment that you can use to probe the chips. We did this on one of the early 21-bit chips. Unhelpfully, because those were asynchronous chips also. And the probe equipment relies on having a synchronizing waveform so that you can measure a repetitive signal and build up your statistics and see a signal which is way down in the noise. This is the first chip I've had, or that I even know about, that has the ability to tell you things about its internal state. It does this with the A to D converter. The A to D converter is a counter. It's driven by a variable, a VCO, variable voltage controlled oscillator. Thank you. I can eliminate one variable by locking the voltage to ground. That is one of the calibration options on the A to D. You can look at ground, you can look at power bus, you can look at a signal coming in from a pin, or you can turn it off. I haven't gotten beyond looking at ground. There's no problem with the A to D. It works fine, giving you up to 12 bits of signal. At ground, the frequency is high. At VDD, the frequency is low, and in between there's a ramp. And you can get many bits of resolution. I want to get 18 bits of resolution. That seems a nice round number to settle on. And what I find is you get below 10 or 12 bits, and you get noise. You don't read the same value twice in a row. This is not unexpected. This is an analog signal. This is a circuitry which is trying to figure out what the signal is. Oh dear, that won't do it all. So you'd expect some variation. You'd expect the variation to be Gaussian, and it's not. Rather than seeing a signal like this, where this is a histogram, and these are the counts, which I read from the A to D, and these are the number of each value I get. I might read 1,000 samples, plot them, and see what the distribution looks like. It tends to look like this. Bimodal, perhaps multimodal, with all kinds of. And I don't know what that's all about. I don't know where the variability can come to cause that kind of behavior. On the other hand, it is well down in the noise. And if I have a few millivolt variation in the internal power bus, it might account for that. And that's what I'm trying to chase down. I'm trying to see what can account for it, and thereby what the internal environment of the chip is. Sorry? Yes, it has different effects. The counts change, but the basic bimodal distribution doesn't change. I've come up with a strategy for correcting the problem. With this kind of a curve, you can average. Add all your signals together, divide by the number, and you get the value of the mean, which you might assume is the peak of the distribution curve. In this case, what I'm doing, and what I just did the other day, I record the distribution, and I search it for the peak, and I record this as the value of the signal. Now, as long as this peak is consistently the highest one, I'm going to be okay. I haven't quite reached that nirvana yet. I've got a situation in which I've got this kind of a distribution with two peaks at the limits of my histogram. And I can switch back and forth between them. But I can't consistently rest on one, because when I sit on this one gets bigger. And so I see it. And when I sit on this one gets bigger, and so I sit on it. And I've got to solve that problem next. So that is the context. Now I want to show you what I did to achieve these histograms and what I did to achieve 1 part in 4,000 stability. If I carry this out really, really well, it's a very sharp peak. It's plus or minus 1 count from the peak. That's a good measurement. That's what makes me think I'm going to get to 18 bits. Plus or minus 1 count in 18 bits is 0.00, 0.01%, some small variation. What I have is a 144, no, 40, another 40. I've got actually 9 40s, but I'm only using 2 of them. This one is reading VSS and passing it across to this one, which passes it across to here and up to here, and it goes out RGB and puts up a display of the histogram so I can see what I'm doing. I was passing every signal through. And that isn't what I wanted to do in searching for the peak of the histogram. What I wanted to do was insert in this data path two nodes. One node takes in the input signal and clips it, subtracts a base point and clips it between 0 and 31. Then it passes a signal to the next node, which constructs a histogram. 32-point histogram with code to zero the histogram, increment the histogram, and return the maximum of the histogram. And that code takes the remaining space. This is what you can do on the 40 or on the 144. You lay out a path for data to follow, and what these nodes were what we call wires. All they did was read from the left and write to the right and just pass the data through, because the data had to get over to here to where the analog RGB nodes were. So there is very often a necessity to move data across the chip. Given you're doing that, it's very easy to alter the data along the way. So the way you read data is, say, fetch against the B register, if the B register is pointing to here. And the way you write the data is you say store, where the A register is pointing to the right. Now you have to say write A store in order to set the A register. And you already somewhere earlier said left B store to set the B register. Having fetched it, I can just send it out. This is what the wire would do, all by itself. Now here I put in an over dot plus 0 max 31 min. And on the stack I had minus 3860 as the center, not the center of the histogram, but the left edge of the histogram. So it cost me almost nothing to do this work. But it was more code than I could fit in one node, so I had to break it into two nodes. But there's no reason not to break it into two nodes, because I've got the nodes sitting there anyway. They're even drawing power. I may as well take advantage of it. Over takes the minus 3860 and subtracts it from the value I fetched. 0 max clips it at the bottom, and 31 min clips it at the top. And it sends it out and repeat. And, no change required in the remaining part of the code, which was actually going to display the data. And I have the functions max and min. I don't know if you've seen them, but they are in ROM. They are in ROM? Probably in ROM. And they're on our website, and you can, max is something like, it's clever, minus over dot plus minus if drop semicolon then plus semicolon. I think that's what it is. If you work through some examples, you can see that in fact will return the maximum of two numbers. Min is exactly the same, except you swap the drop and the plus. What happens when the two values are equal? Doesn't matter. It goes one way or another and comes up with the same answer. But I'm still getting these noise, And I spend hours just staring at the screen thinking, where is it coming from? What is it trying to tell me? And of course, in staring at the screen, I said, 0 max. That is an ugly way of doing things. So I defined a word 0 max to specifically test for 0. In fact, Jeff or somebody alluded to that earlier, which is much simpler. It is a minus if, dup or, then semicolon. So if the number is 0, if the number is negative, copy it and exclusive OR it to itself and produce a 0, and you're done. This is much simpler than this. It saves 2 words. Some of that messy code there, and this literal 0 here. Only 2 words. This turns out to cost 3 words. You can do even better if you put that code in line instead of calling it, because then you don't have to have the call instruction. I find that these computers are fun to optimize that way. It doesn't make a whit difference in the whole world whether I use the short version or the long version. But I'm compelled to optimize where I can, make it as small and as simple as possible. And so I did. I don't see any way. Well, there are ways of doing 31 min. I mean, you can mask instead of subtract. But I don't think it saves any code. The next step along the way is equally interesting. The code for histogram. I cannot write it all down, and if I actually put it on the screen and showed it to you, you wouldn't look at it carefully enough to appreciate. So I will try to isolate the interesting part. I have to look through 31 values, and I do a dup or a store to set A at 0. My array is stored between 0 and 31. That's the natural way of doing it, simply because you can always get your pointer set to the beginning of the array without working very hard. Fetch a value, call a function called maxi, and repeat. Put another dup in here. Well, doesn't matter. Once you come out the end, this takes in a number and compares it with what's on the stack and returns the value of the maximum position it sees. Maxi is interesting. It's just like max, except it has a different stack effect. And it starts off with a minus over dot plus minus if. Then, if this is the case, I can't remember which it is. If this is the case that it is larger, you want to remember where you found it. And where you found it was at A. So you just put down the A register, which is where you were, and then you do an over, or a drop. There's a drop here, I think. And then an over to get the value. And you started off with a value of A and a value of the max. And you gave it another value, and you end up with a new value of A and a new maximum. two things on the stack. The saving grace is that your index is in A instead of trying to pick it off the loop index. If that's not the case, semicolon, then drop. Leave things as they were, and you're finished. And when you're all through with this loop, you say drop, which gets rid of the actual value of the maximum, which you don't care about, and leaves you the index on the stack. So now you know where the peak was. Two things you can do when you're at that peak. You can record it as the value you're going to conclude is the correct value for this analog signal. Or you can take the peak value and look at its two neighbors and fit a parabola through them and interpolate to a fraction of a bin size. That's a simple calculation. So that is how I plan to get my bits once I get into a situation where I've got a single peak that dominates that I can track. And so it goes. Yes. Now what I find, this was not the obvious, but what I find is that if I measure this temperature, this value, it changes with temperature. The chip gets colder, it counts faster. If the chip gets warmer, it counts slower. So I've got the data from which to calibrate temperature. I assume it's going to change linearly with temperature. That remains to be seen. I have to have an environmental oven in which to calibrate it. What I've done is measure room temperature and set the one value, then freeze the thing a little bit and set another value, and it's not very accurate, but it proves the point. I'm presently looking to get a 10th degree resolution. 100th degree I think is achievable. 1,000th degree would be really nice, but I don't know if I can, if it's that sensitive. What's got to be happening in order to create this noise is that the voltage on the power bus is dipping. That's the only thing that can be, that's the only variable there is. The ground plane is solid. The voltage is changing a little bit. As the voltage changes a little bit, the counter, the VCO changes a little bit, and I get noise. It can, yeah. Yeah. That's the next topic. It makes sense. And when I get the temperature pinned down, then I'm going to look at the voltage and then do the same analysis with it and see how much the voltage changes, being able to compensate the temperature and eliminate that variable. So voltage and temperature will be under control. Now, there are two ways of measuring, of determining the number of measurements I'm going to make to put into my histogram. And the way I'm doing it at the moment is I count, I have 1,000 4 X loop. I just count 1,000 times and read the A to D and repeat. This is cute because the 4 next loop is going to vary with temperature. And the VCO is going to vary with temperature. And I argued with the lawyers at the deposition about this. They're not going to vary the same with temperature. There's going to be a differential effect between them because you only get a ring oscillator that tracks your CPU if it's made out of the same transistors because the transistor size is going to affect the variation of temperature. This is not obvious, but it is observed. I've seen it happen, and so I know that that effect is there, that the count I get doing this will vary with temperature, probably linearly. The other way of doing it is to time the A to D with a crystal oscillator, with a crystal. And I've done that, and I get a measurement which varies in the same way. I couldn't see any difference in the behavior of the histograms. And since it's easier to time things with a Micronex loop than with a crystal, that's the way I'm doing it at present. When I get this pinned down or whatever, I'll try the crystal again and see if it is better or worse. This is all in aid of a real application, which is battery management. You maybe perhaps aren't aware of how a car battery is built, one of these electric vehicle batteries. They're built out of a whole lot of little cells, thousands of little cells. Basically, just stack them up. And the laptops have got 6 cells in them or something like that. They're made of cells of cells. You want to measure the temperature of these suckers. So we put a GA4 on each battery, and it accepts the ambient temperature of the battery as its speed, and you can all measure these things. If you can measure them very accurately, like 0.001 degrees, you can track the condition of the battery and say, look, this battery is getting a little bit warm. It looks like it's going to exceed its limits in 3 weeks, and maybe we should warn the driver about it. So an accurate temperature measurement offers all kinds of interesting things. Supposing I have the chip which is monitoring temperature, room temperature, and I put my finger near it, and it detects the temperature of my finger in the vicinity to 1/1000 of a degree. I've got a touch contact. Fun. In general, measuring things accurately is fun. I learned that as a physicist. I'm trying to carry it out in my career as a technologist. Pipelining, clipping histogram. And another example of that, change of pace, are the Voyager spacecraft. I don't know if you remember them. You probably all do because you're of the right age, but we sent 2 spacecraft out of the solar system 20 years ago? 30 years ago, and they're still going. That must have been 40 years ago then. They're still going, and they're still being tracked with Doppler signals. I don't think we bounce signals off them, but it is broadcasting a continuous, I think it's a continuous wave, and we're monitoring the frequency very accurately, so we know their velocity. And they are 50 AU away, way out beyond Jupiter, or beyond Pluto. And there's a huge scandal about them because they are not following Einsteinian gravity. Gravity field is supposed, the gravity force is supposed to be decreasing as 1/r² as they go out there, and it isn't. Nobody knows what's going on. Could be dark matter. Could be quantized gravity. Could be alien space probe tracking it. But it's fascinating. And the reason we know this is because they've been tracking it so long and so carefully, and it just isn't behaving correctly. Then there's the string theory. String theory suggests there are 6 additional rolled up dimensions to our universe that we aren't aware of. And it predicts that gravity is so weak because gravity is leaking into those extra dimensions. And those dimensions are probably of the Fermi length, which is 10 to the minus 33rd centimeters or something unknowable. So, by gum, they're measuring gravity with a torsion pendulum at very small distances, just to see what happens. Is gravity leaking away as you get smaller and smaller into these tiny extra dimensions? And so far the answer is no. They've gotten down to 0.2 millimeters. They know the force of gravity at 0.2 millimeters, which is a neat trick to measure. They have a prayer of getting to the Fermi length. They think they can probably get to 0.1 millimeters, which means that these coiled up dimensions, if they exist, are smaller than that. So we're getting an upper limit and useful information. So I'm thinking, in the tradition of a physicist, that if I can measure temperatures cheaply and accurately, I may be able to do something useful with it. Hope goes on. Another thing I'm doing in between my bouts with Colorforth and lawyers is reading about biology, molecular biology. Molecular Biology of the Cell by Albert. And it's a book that is so heavy, if I sit reading it too long, my hand hurts from holding it. Currently I'm studying. I'm trying to learn from it, so I'm reading it more carefully than I would maybe read other things. But I'm not working the problems, which is a scandal. You're supposed to work the problems. They tell you up in front, you gotta work the problems. But I'm learning about actin filaments and microtubules and intermediate filaments, the things that make your cells have shape instead of blobs. The 144 is a complex computer. It is, you want to approach it cautiously. You want to program one node and another node and work your way in, and not just jump in and write a great big thing because it's not going to work. It's complicated in that regard. 144 independent things are complicated. The cell is full of thousands of proteins, all of which act independently of one another, asynchronously with one another, interacting with one another to do miraculous things, the product of evolution. The parallel between this computer and its successors and the cell or a neuron is compelling. It's fascinating. We're going to be able to do some really exciting things that the real world can't do or won't do because it would require a room full of PCs or a supercomputer that nobody can get access to. The Chinese have the record for the supercomputer world of teraflops or something, petaflop. But they don't have any software. They've got the computer with nothing to justify it. My dream is put 9 of these guys on a board and stack up 10 boards with wires running between the boards and between the chips and all, and have, what's that, 9 times 10, 90? 100 computers. That's 100 times the MIPS, 100 times the amount of code you got to write for it. But maybe we could simulate some galaxy evolution or some quantum mechanics, or, hey.
That was the question I did ask. Would it be possible to solve differential equations using
Oh, yeah, sure. If you've got, I mean, the 140, it doesn't have any memory, so you can't store very much state information. But you can do the calculations, and you can do 144 of them in parallel. So you can really grind out partial differential equations. In integer arithmetic. Yes, but they do something fundamentally wrong. They use floating point arithmetic because temperatures are in megadegrees and densities are in grams per cubic centimeter or something. They don't scale things properly. And they use temperature instead of log temperature, which I've never understood. So I think there's great opportunity for doing something imaginative. Yep. If they do, yeah. Good cluster, they would. Unfortunately, there's not a market for a large number of chips in that application. But still, I would like to do one as a proof of principle and may give it to an astronomer, or maybe they'd even pay us money to program it. Yeah? Well, you sound like one. Hey, all it takes is a Haypress Creek board, and you're off and running. Okay, that runs out of my time. We're supposed to go to dinner. But I will take questions if I haven't answered them all. Yeah. Magic. No, there's a lot of contributing factors. Probably the most obvious one is that you have zero argument operands. Your instructions can be shorter. Shorter instructions pack better, use less memory, less silicon, less area. You're squeezing it that way. If you have registers, addressable registers, you've got to provide the addresses in the instructions. Instructions get longer. Also, calculation especially, the numbers pop right up on the stack and they're right there where you need them. You don't need to go off and get them anywhere. This code, which I had up there before, I showed a number on the stack. That number on the stack had to do with the clipping of the data that came in and went out. I couldn't keep that number on the stack if I was doing something more complicated, because other numbers would get on a stack and it would become a stack clumsiness. But with 144 computers, you've got 144 stacks, 144 ALUs, and you can afford to waste them or exploit them in very convenient ways. Every calculation can have its own stack. You don't need to share the stack with something else. You don't need to have variables to store things away and fetch them back. So that helps. Right. It's the 144 nodes is too many. Nobody knows how to use them, even Michael. But It doesn't cost anything. They may as well be there. And if you can use them, fine. If you can't use them, ignore them or treat them as wires. All a wire does is introduce latency. It doesn't affect your bandwidth in the slightest. Yes, sir. Yeah. Well, he's pretty much simulated an orchestra. And where do you go from there? But I would like to experiment with different kinds of sounds. I think the sounds you get from electronic synthesizers are ugly. The sounds you get from instruments have been around for hundreds of years. There ought to be something in between, very pleasing sounds that no one has heard before. And that would be fun to explore. Yeah, probably 100. Now that's not necessarily 100 instruments because you want the overtones and so forth, but we're getting to the point where you can get some very impressive sound. I would like human speech. I don't like my voice particularly. I'd be happy to speak into a microphone and let the computer speak my voice for me and craft it so that I sounded just the way I think I sound. There'll be a market for that. There's a market as soon as you can enhance people's ability to communicate.
What are some of the high volume applications you see for process simulation?
Yeah, I don't know the 144. I do know the 4. And the intriguing application is for Christmas tree lights. You put a GA4 on each RGB LED, string them in a line, and let people make dynamic patterns, program their own dynamic patterns on their own PC to run their Christmas tree lights.
You're getting into art.
Hey, yeah. And maybe they could all sing at you too. Each light would make a little sound and the tree would jingle.
I'd like to thank our speakers, all of you, and in particular Chuck for his fireside chat.
Dead.
Before you bolt to the door, I have to close the front of the room. But before we do that, Jeff has a short presentation. I wanted to present this to Chuck to put up on his office wall. He says a 144 node is too much to deal with, so here is 120,000 processors on a piece of silicon, framed and with his name.
Very nice. That's 24.
All right, here's the way it works. Everybody get to the front of the room. First, we're going to video everybody.